So I think we discussed the line is a connected set, right?
In the last lecture.
Yeah. We did, right?
Yeah.
Okay. So taking a clue from that, we can show that the rationals are dense in real numbers. What does it mean? So what we want to, what we can use it to show that. So given or having proved the line is a connected set, we can show rationals are dense in the reals. What does it mean? It means the closure of rationals is R itself. R itself. Any interval AB contains infinitely many rational numbers and any real number is a limit point of or for the rationals. Now I want to show something else to you. You will prove this in higher classes. It is just a few steps away. A little note of importance. Note: if we had restricted our attention to the set of rationals, we would have found that the LUB property, right? LUB property failed, and the rational line, by rational line we mean a number line which consists only of rational numbers. Rational line is not connected, meaning there are gaps. So who will fill the gaps? The irrationals.
Yeah.
This then becomes the starting point of analysis. For, let us say, Q equal to A union B, right? We are talking of connected sets, so we first talk of two sets. A and B. These are a little bit arbitrarily chosen, but you nevertheless it is an example. Rational numbers x with x cube less than 2, b equal to all rational numbers with x cube greater than 2. So both A and B are open, right? Both A and B are open. And disjoint. The fact that A and B cover R. Cover is a technical word, we will use it very often. I think I had explained it to you in set theory. You remember, if we say that let us say S is equal to A1 union A2 union A3, then A1 A2 A3 covers S.
Okay.
Huh?
Yeah.
It will further be used in the case of compact sets, which we will learn very soon. The fact that A and B cover R uses the irrationality of cube root 2 so since no rational number is cube root 2, so since no rational, are you getting it? Number is rather no rational number x satisfies, this is better put, x cube less than 2 or x cube greater than 2. There will be a variation here which I will introduce. I will give you some other example later on. Okay, for now it is sufficient because it is easy. Okay?
The last unit is no rational number x satisfied x plus 2.
Yeah. Yeah.
What does it mean? This doesn't make any sense. Like rational number x satisfied x cube less than 2. Okay, there is no rational number less than.
You are right. Since no rational number x satisfies, you are right, x cube equal to 2. Now it is clear. The fact that A and B cover R uses the irrationality of cube root 2. Since no rational number x satisfies x cube equal to 2, everyone must obey either, now this makes sense, x cube less than 2 or x cube greater than 2, right? This is better. Yeah, good. Okay, so now let's see where this. So intuitively the LUB property tells us that there are no gaps in the number line. So what does it mean, Surya? To every real number there corresponds a point on the number line and vice versa. Okay? There are no gaps in the number line, or we say the reals is a complete field. So now since we are learning not just the line, but we are learning En, right? The Euclidean n-dimensional space. But if you consider E2, what is it? It's a product of Cartesian product of R cross R. If you consider three-dimensional space, it is a product of E2 cross R. Right? So basically, the properties of En depend on the properties of the reals of the real number line. That is why we are going to such a level of detail. Follow? Okay, so now the next question, having understood this connection, the next question is natural question that arises and which you know as a thinker is what property of n space, Euclidean n space, corresponds to this property of the line, of the real number line. Right? It's a natural question. Okay. So the answer is actually there are quite a few equivalent properties. We will talk about this. We consider the nested set property. Again, because the emphasis for this discussion or the course is that we develop a geometric viewpoint, we will not immediately go into a proof of this, how to derive the nested set property from scratch. Okay? But I will merely state it and use it to derive further interesting topological properties of the real number line. So what does it say? The nested set property. The nested set property. Let C1, C2, C3, so on and so forth be closed and bounded sets. non-empty, of course, non-empty, such that C1 contains C2, contains C3, so on and so forth. Then there is at least one point which belongs to all the sets Cn. So what is of importance here in the hypothesis? The set must be closed as well as bounded. There is an exercise in which I am asking you to show that if either one of these conditions is not satisfied, the nested set property fails.
Okay.
So I think you can do it by producing a counterexample.
Okay.
Hmm?
Okay.
So we now come to a very interesting theorem which I think you will have in your next semester. It's the Bolzano-Weierstrass theorem. Bolzano and Weierstrass were two mathematicians. Okay. Weierstrass is considered to be one of the founding fathers of analysis. Cauchy Weierstrass, German chap. He was a school teacher till about 30-40 years, doing research on his own in the night. Bolzano, Weierstrass. I think one of these guys, Weierstrass or Dedekind, came up with a nice definition of a function that we use nowadays. We use it as if it is obvious. I have one student who tells me, sir, it is very simple, it is obvious. Therefore, he doesn't write any proof like Ramanujan. And what happens is that his grades fall all the while. Every bounded infinite set S has at least one limit point. Okay? So as my algebra teacher used to say, what is the meaning of the question? The meaning of the question is, number one, to produce a point such that every neighborhood of it contains infinitely many points in S. Right?
Yes.
So, and Surya, when you write the proof, you do have to mention that. Immediately don't start writing the proof. Okay, this is also one of the aims of this course that I am giving you. A little rather formal ways of writing formal proofs. Okay? So, proof means to prove that we have to produce a point P with the property that every neighborhood of P contains infinitely many points of S. So we take a simple case first. We take a case when S is E2. This is the Euclidean space, because we can use diagrams, which I have been telling you since many years. Diagrams are always useful. Okay, now what do we do? Now I think you too can produce the proof if I show you a little statement. See, if a set is bounded in any fashion, it can be bound by a rectangle, right? This is the idea we use. So what we say is, since the set S, think of the plane only, is bounded, we may assume that it is completely contained in a square Cn or C0 of side L. So here what I claim is something like this, right? Of side L, I call this as side C0. Now comes another little trick. We divide C0 into 4 squares all equal squares, this way, such that one of these smaller squares contains infinitely many points of S. Infinitely many points of S. So we can name the squares also, and then take this. Suppose this is the square which contains infinitely many points. Divide it further into 4 squares. Select an arbitrary square which contains infinitely many points. Go on subdividing the region further. So ultimately you get a chain of sets. Hello? Hello? Are you there? Surya, you switch off your video.
Okay. Yeah.
Okay, did you hear the argument? I will repeat the argument. Huh?
Yeah.
Okay. Okay. So have you made notes?
Yes, sir.
Okay, great. So now what we get is a sequence of sets or squares C1 containing C2 containing C3, so on and so forth, or not subset, it is the opposite. Yeah, right? Containing Cn, there's an infinite chain of squares.
Yeah.
So by the bisection process, we see that each side has length L by 2 raised to n. Now we use nested set property. See, the squares are closed and bounded, so we can use the nested set property. There must be a point P which lies in all squares or sets, in all sets Cn, right?
Yeah.
Now what is remaining to be proved, Surya? We have to prove it is a limit point.
Yeah.
First we have found a point and then we have to prove it is a limit point. Okay? So what we do now is take any neighborhood U of P U of P got neighborhood U of P bar of, let us call this neighborhood a neighborhood U of P bar, which itself is a disk with center P. As I draw the diagram, it will become very clear, and radius epsilon. Okay, so I will draw the diagram first. Yes, this is better now. One of my students, hello Surya,
Yes, sir.
one of my students has taken applied math in UCLA.
Acha.
Yeah.
Okay.
So she's also back in India, in Bangalore after one semester. She wants to come and meet me.
Okay.
She used to hate math. I wonder why the. Yeah, she used to hate me also. I wonder why there is a change of heart. Is it just a change of heart or a change of intellect? I don't know. I hope it is both, otherwise, you cannot survive. In applied math, especially. So, this is the small square. We take a disk with center P, radius epsilon. This is what I call the neighborhood U. Is it clear now? Okay. So now, in radius epsilon, when n is sufficiently large, I will make a little comment on this proof. When n is sufficiently large, say with L by 2 raised to n less than epsilon by 2, the set U, the set Cn which contains P bar must in fact lie in U, since Cn contains infinitely many points of S, so will U, right? So will the neighborhood U. So we have proved, hence every neighborhood of P contains points of S and P is a cluster point for S. Yeah? We next come to the theorem that you have proved in your analysis teachers will prove it in your next course, next semester also. The Honey-Borel theorem. It is a direct and easy consequence of the nested set property. Honey-Borel. Oh yeah, before we start this, in the last proof we used words like infinitely many and sufficiently large, right? So these are the things which are given formal shape in a formal analysis course.
Okay.
Right? Right now we are just trying to develop a geometric insight into the nature of the real number line. Okay? So now this proof is a little bit with flooded with symbols, so be a little bit slow. let C be a closed and bounded set in the Euclidean N space. You're gone. Okay, there's a net connection problem. Are you there now?
Yes, I cannot see the screen though.
Yeah, okay, now you will. Let me know.
Yes, sir.
Okay, let C be a closed and bounded set in the Euclidean N space, and let U1, U2
So I can't see the board now. I can just see your screen on the board.
Oh, okay. I think then your bandwidth is low over there.
So will you start it again?
Sure, I will.
Sharing the screen.
Yeah. How about now?
Yeah, it's beginning. Yeah, I can see your screen on the board now.
Now? Can you?
Yeah, that's fine.
Let U1, U2 be a collection of open sets. Be a collection of open sets which together cover C. Then there is a finite subcollection of the sets U sub I which together cover C. Follow? So once, yeah.
That you want you to use to get collection of open sets with
Together cover C. Then there is a finite collection, subcollection of the sets U sub I which together cover C. Cover C. What it means, Surya? C is a closed and bounded subset of En. Okay. But C is also a subset of C1, union C2, union C3, so on and so forth, union Cn, the chain continues. Okay. Now out of these there exists a finite, I have written C instead of U1, U2, but you will understand. Out of these there is a finite collection C1, C3, some CP, CQ, which covers C1 union CP union C3 union CQ.
Okay, fine.
Okay? Such sets are called compact sets. Compact.
Okay.
So one of the things we are going to use here is use a exercise result. If C is closed, and V is open, then C minus V is closed. Proof. Construct some new open sets Vn. Let V1 be equal to U1 V2 is equal to U1 union U2, V3 is equal to U1 union U2 union U3 equal to V2 union U3, right? And in general, the set V sub Vn plus 1 is equal to Vn union Un plus 1. Now we have constructed the sets, we are rigging the proof. The sets Vn are all open and form an increasing sequence V1. So V1 V1 is a subset of V2, which is subset of V3, so on and so forth. The collection of all these sets, Vk together covers C. Together covers C. So we continue to rig the proof further. Put U1 equal to put C1 equal to C minus V1, C2 equal to C minus V2, C3 equal to C minus V3, so on so forth. Ck equal to C minus Vk. By the exercise result, we know Ck is a closed set since the set U is bounded. The sets Ck are also bounded, right?
Sir, yes.
Since the set C, you are right. Your suspicion was right. Since the sets wait. Hold on. I am sorry. Could you please repeat the statement I gave? In my handwriting, I got confused between U and C. Let C be a closed and bounded set in En, and let U1, U2, so on and so forth be a collection of open sets which together cover C. Okay? So now it is right. Since the set C is bounded, the sets Ck are also bounded.
Sir, like the question, what is supposed to prove is that if C is closed and B is open, then C minus B is closed.
No. We are using that result already in the Sunny-Borel theorem. Okay? Yeah. Where did we use it? We used it here just now. Follow? It was one of the exercises I think given to you. Otherwise you can prove it later during the day. So since the sets Vk expand as k increases, the sets Ck contract as k increases. See, there is a beautiful geometric picture here, right? Hence we have again a nested family of closed and bounded sets. C contains C1, contains C2, so on and so forth, Ck, and so on and so forth. So what does the question arise? What is the next natural question that arises? Because we want to use the nested set property, could there be a point that lies in all the sets? Right? Could there be a point that lies in all the sets? If so, Q would belong to such a point called Q would belong to C but would not lie in any set Vk. But the sets Vk together cover C. So this cannot happen. So this cannot happen. What cannot happen?
We cannot have a point Q which is just the same amount of instance.
Which is there in all the sets. The only way out is to have one of the sets empty. One of the sets empty. So if C, let us say Cm equal to the null set, empty set, then Vm contains C and the sets U1 U2 UM form a finite subcollection which together covers C, and any set which satisfies the unimodal property is called a compact set. So this is a compact set AB. You will have to prove it. It is question number 7 in your assignment today. Nested intervals on the line. Okay? We'll meet either tomorrow, I will phone you in the night, or we will definitely meet day after tomorrow if we don't meet tomorrow.
Morning.
Yeah, same time. Okay, I will confirm tonight. Okay, thank you, bye bye. I have already sent you the email.
Yeah, I just saw it. Just for the lecture started.
Yeah, okay then. Bye bye.
Thanks a lot. Bye.
Bye bye.